Good morning, children. Sairam. Today we'll be starting with how we can predict the extent of a chemical reaction using the value of Kc. That means the equilibrium constant. See, if suppose the value of Kc is greater than 10 raised to power 3, that means the product predominates. That means the product is produced more and the reactants are left very less. That means such reactions are very useful. If Kc is large, the reaction proceeds nearly to the completion. Now, let us consider a chemical reaction in which hydrogen and chlorine react to produce hydrogen chloride. For this reaction, the value of Kc is 2.4 into 10 raised to power 47. Whereas for it is 4.0 into 10 raised to power 31. If the reaction takes place between hydrogen and bromine, for this the value is 5.4 into 10 raised to power 18. That means we have higher values, so the reaction is useful. More quantity of product is being formed. If suppose the value of Kc is less than 10 raised to power minus 3, that means the reactants predominate. That means even after the establishment of the equilibrium, only a little quantity of product is formed. That means such reactions are of no use for us. An example of such a reaction for you is nitrogen and oxygen. When nitrogen and oxygen react together to form NO, the value of Kc comes out to be 4.8 into 10 raised to power minus 31. Minus 31 is very less. That means the value of Kc is very less. So, we can say that the quantity of product formed will be very less after the establishment of the equilibrium, whereas the quantity of reactant left will be more. So, such reactions are of less use. The third thing is, if the value of Kc ranges from minus 10 raised to power minus 3 to 10 raised to power 3, we can say appreciable concentration of both reactants and products are present. That means such reactions are, you can say, useful, but at the same time more quantity of product is also less. For example, for the reaction between hydrogen and iodine to form hydrogen iodide, the value of Kc is 57.0 at 700 Kelvin. Similarly, if we see the reaction between we can say the gas phase decomposition of N2O4 to form NO2. Here also the value of Kc is 4.64 into 10 raised to power minus 3 at 25 degrees Celsius. So, such reactions, appreciable quantity of reactants and products both are left even after the establishment of the equilibrium. Now, you can see this. You have to remember from this that Kc less Kc, if it is greater than 10 raised to power 3, that means the value of Kc is more and products predominate. This side, the value of Kc is very less, reactants predominate. Now, another thing is the direction of a reaction. If the equilibrium is not established, but we know the concentration of the present time, we can calculate the value of equilibrium. And we are knowing the equilibrium constant value also. We can find out the reaction will go in forward direction or in backward direction by calculating the value of reaction quotient QC. Now, what is reaction quotient QC? It is again the product of molar concentrations of product raised to the power equal to the stoichiometric coefficient divided by the product of molar concentrations of reactants. Now, this is not calculated at the time of establishment of equilibrium. It is at any instant when the reaction is taking place. We calculate the value of QC. If it is less than Kc, that means the reaction will proceed in the direction of the products. Here, if it is less than QC, if it is less than Kc, the reaction will proceed in the forward direction. But if QC is greater than Kc, that means the reaction will now proceed in the backward direction. QC is equal to KC, that means the equilibrium has been established. So this reaction question tell you about the direction of the reaction. That means if reaction quotient and Kc, the equilibrium constant, both are equal, that means the reaction is now present at the equilibrium concentration. If QC is less than Kc, the reaction will go towards the product. If QC is greater than Kc, the reaction will go towards the reactants. Next is calculating the equilibrium concentrations. Now, how can we calculate the equilibrium concentrations? See, it is very easy. First of all, we have to balance the chemical equation. Then we have to make a table that lists the substances which are present in the reaction. We have to write the initial concentration, the change in concentration on going to the equilibrium. The third thing is the equilibrium concentration, and after that we have to write down we have to make a table and write X as the concentration of one of the substance that reacts on going to the equilibrium. Then we have to use the stoichiometric coefficient of the reaction to determine the concentration of the other substance in terms of X. An example also will solve. You can see the example. Suppose we have 13.8 gram of N2O4. It is placed in a 1 liter of reaction vessel and the temperature is 400 Kelvin. It is allowed to attain the equilibrium and form 2NO2. Now, the total pressure is given, it is 9.15 bar. We have to calculate the value of Kp, Kc and the partial pressure at equilibrium. Now children, we know that PV is equals to nRT, the ideal gas equation. The total volume is 1 liter and the molar mass also of N2O4 is 92 grams. And we can calculate the number of moles. It is equal to given mass upon molar mass. Given mass is 13.8 and the molar mass is 92. We have got the number of moles, that is 0.15. Now the value of gas constant also we know, it is 0.083 in bars. Temperature is given. Now putting all these values here, we can calculate the value of the pressure. Now we got the initial pressure of N2O5. The initial pressure of NO2 is 0 because at that time no quantity of NO2 exists. Now at equilibrium, X is the pressure of NO2. Now as we have the stoichiometric coefficient 2, so we'll multiply it with 2. Now the quantity of N2O4 left will be the initial pressure minus X. Now total pressure of both the reactants, or you can say the total pressure of reactant and product will be equal to pressure of N2O4 plus pressure of NO2. Now both the pressures we know in terms of X, so we can calculate the value of X. Now we have got the total pressure. This is your total pressure. This is your total pressure, and we'll calculate the value of partial pressure subtracting from the total pressure. We got the partial pressure here. Now you can simply use the equation Kp is equal to Kc RT delta N to calculate the value of Kc. So it is simple. Now next is the relationship between K, the reaction quotient Q, and the Gibbs energy G. Children, this is derivation is not there in your syllabus. You can simply learn the equation delta G is equals to minus RT ln K. This you have to use for the numericals. It is simple. Actually the derivation is not there in your syllabus. Now next I am starting with the factors affecting equilibria. Now children, the factors which affect the concentration, you can say the position of the equilibrium, the change in any of the factors, it is explained by Lee-Chatelier. Now what Lee-Chatelier says, the Lee-Chatelier principle states that change in any of the factor that determine the equilibrium condition of a system will cause the system to change in such a manner so as to reduce or counteract the effect of change. That means if we are changing any of the factor that is determining the position of the equilibrium, then the reaction, or you can say the reaction will balance itself, or you can say the reaction will try to take itself to that direction in which the effect of change is minimized. Now, the first factor that we are discussing is the effect of change of concentration. Now, children, suppose we have got a chemical reaction, like for example, it is H2 plus I2 gives 2HI. Now, for such a reaction, if we increase the concentration of the product, now, for such a reaction, if suppose we increase the concentration of hydrogen. Now, if we increase the concentration of hydrogen, then according to the Lee-Chatelier principle, it will try to balance itself and reaction will go in that direction in which the increased concentration is consumed. That means in the forward direction. So, if we increase the concentration of reactant, any of the reactant, according to Lee-Chatelier principle, the reaction will go in forward direction. And if we increase the concentration of the product, then to counteract the change, to minimize the effect of change, the reaction will go in the backward direction. Now, next is the effect of change of pressure. Change of pressure and change of volume, both are the inverse of each other. See children, let us consider the reaction CO plus 3H2 gives CH4 plus HO2. Now, the effect of change of pressure, it depends upon the number of moles. See, on the reactant side, if we see, there are 4 moles. One more thing you have to remember, that this effect of change of pressure is considered only for the homogeneous reaction in which the reactants and products are present in the gaseous state. If the reactants and products are present in the liquid or in the solid state, then we do not consider the effect of change of pressure, because it does not affect the volume. The volume of liquids and the solids does not change. So, it is considered only in case of the gaseous reactants. Now, we have 4 moles of gaseous reactants on the reactant side and 2 moles of gaseous reactants on the product side. Now, suppose the equilibrium mixture is kept in a cylinder which is fitted with a piston and is present at the constant pressure and is composed to 1/2 of its original volume. Now, if suppose we mix the two, then the pressure becomes double according to PV is equals to constant. Now, therefore, the concentration of the reactants and products have changed and the mixture is no longer present at the equilibrium. So, it will re-establish itself to form the equilibrium according to the Lee-Chatelier principle. Now, as the pressure is doubled, that means the pressure is increased. So, the reaction will shift in the forward direction. Why? Because in the forward direction, the number of moles are less. So, the pressure will also be less. That means if we increase the pressure, the reaction will go in that direction in which the effect of change is minimized. That means go in that direction in which the pressure decreases, and the pressure will decrease that side where the number of moles are less. So, for such reaction where this side we have 4 moles, this side we have 2 moles. If we increase the pressure, the reaction will go towards lesser number of moles. So, the pressure will decrease. If we decrease the pressure, the reaction will go towards more number of moles to increase the pressure. Now children, the effect of volume, change of volume is just the reverse of this. If we increase the volume, if we increase the volume, the reaction will go towards more number of moles. If we decrease the volume, the reaction will go towards the lesser number of moles. Next is the effect of change of temperature. You can understand this in an easier language. Now, we know that if a reaction is exothermic in the forward direction, the same reaction will be endothermic in the backward direction. If the temperature is increased according to Le-Chatelier principle, the reaction will go in that direction in which the effect of change is minimized. If pressure is increased, it will go towards the direction where the increased pressure is absorbed. So, endothermic direction. Endothermic direction can be either backward or forward. You have to see by checking the value of delta H, the sign of delta H. If it is minus, that means it is exothermic. If it is plus, that means it is endothermic. If the temperature is decreased, then to balance this, the reaction will go in the direction of the exothermic. Now, effect of change of addition of a catalyst. See children, we know that the catalyst increase the rate of a chemical reaction, but we have to remember that the catalyst increases the rate of the forward as well as the backward direction. So, we can say the catalyst does not affect the position of the equilibrium. So, we can say the catalyst do not have any effect on the equilibrium position. Now children, in the next presentation we will be starting with the ionic equilibrium in solution. Till then, kindly note down these factors affecting the equilibrium and the Le-Chatelier's principle. Thank you and Sairam.